Ladies and gentlemen, we are going to build a model that is going to have the essential elements of infectious disease that we've seen before. So I would like you to create within this model 3 stocks, susceptible, infective, and recovered. And you're big boys and girls now, so you should have a good sense about how to add those in. And then there will be a set of flows that are going to join them. And for the moment, these flows will just include a flow from susceptible to infected, or to infective, I should call it, and infective to recovered. Okay? So I'm going to go to the palette now, and you shouldn't need much hand-holding on this, but I'm going to create a susceptible. I'm going to create a infective, and I'm going to create, infective 3, infective, and I'm going to create a recovered stock, okay? Recovered, there we go. Next, I'm going to join them up by flows, and this is going to be called infection. And I will, because it extends beyond here, just revector it to end there. And similarly, from infective to recovered, I am going to have a flow recovery. Okay, great. Now, I will tell you that we are going to initially start with 999 people in the susceptible state. We will start with initially 1 person in the infective state, and we will start with 0 people recovered. Okay, great. Now, I'm going to tell you further that recovery here is a first-order delay. What does that suggest that we need? One of 2 types of parameters. Give me the 2 types of parameters that might be associated with a classic first-order delay. We could either have either phrase it in terms of it actually covered three sets of parameters that could be used, but 2 of the earliest ones we covered were what? With a first order delay, what is the formula for recovery? Either what or what? Rate. Good. Excellent. Wade got it exactly. So a rate, and then is that rate multiplied by the stock, or is the stock divided by that rate? If it's a rate, if it's a probability per day, say, that someone recovers, would recovery be multiplication of that rate by the number infective, or would be the number effective divided by that rate? Multiplication is right, because it's a probability per day. And so if infective is measured in persons, this flow is going to be measured in what? If you have a stock and you have a flow out of a stock, the stock is measured in units of X. The flow has to be in measures in units of what? Or in dimensions of what? Per amount of time. Yeah, exactly. So like this would be persons per day in this case, okay? So if we have persons per day, it has to be infective times a probability per day. Probabilities are dimensionless. So the fraction of coins that end up heads, so you have coins over coins. So there's it's a dimensionless number, as we call it. It's a unit dimension. It doesn't matter what dimensions we use to measure coin flips. It's a fraction of coin flips doesn't need to change because as we change our dimensions. We'll talk more about that later in the semester. But we could have a per day chance of infection. Alternatively, what could we have? So Wade's suggestion is bang on. We could have a probability per day. Alternatively, what could we have? We could have a mean time with disease. Let's have mean infectious period. How's that? Mean infectious period. Okay, and that will be in days. And we'll make it 10. Okay, great. And then we will put in a link from mean infectious period to recovery. And what else does recovery have to depend? Just logically, it has to depend on what? On infective, yeah. If there ain't nobody who's sick, there ain't no one who's going to recover, right? Yeah, okay. So recovery here is given by infective divided by mean infectious period, okay? Mean infectious period. There we go. Okay. Infective divided by mean infectious period. Great. Right? So we have people divided by days. So it's people per day, recovery. It all fits together. It congeals. It kind of is coherent. Great. Okay. So I did the easy one. For infection, this is a nonlinear model. What do we want? Give me a few of the parameters we'll want for the infection flow. What must that depend on? Good, yeah. So probability of transmission, I put a space there, probability of transmission. And I can make it much longer from a susceptible to an infective or something, but I'm just going to say probability of transmission. And then what else would it depend on? So that might be affected by like hand washing, right? If I'm really good at washing my hands, I'm an infective, but I might not pass it on if I wear a mask when I am ill. Then I'll have a lower chance of passing it on. If I share needles, I'll have a higher chance of passing on. So this probability of transmission is something that can often be affected for a person. And what's the other thing that it would depend on? Contact. Yeah, contact rate. Contact rate. How many contacts per unit time I have, right? Contacts per day. Okay, great. So, ladies and gentlemen, let us make the probability of transmission 0.04, and let us make the, contact rate, not contacts rate. Contact rate here will be, let's say, 10. Okay, great. Great. Okay. Excellent. Excellent, excellent, excellent. Now, I am going, just for didactic purposes, to have a force of infection here. I'm going down a trip down memory lane here to make sure you're recalling these things. What is the force of infection? Or maybe I can ask operationally, how does the number of people infected per day depend on what does it depend? Give me two things on which it depends. Excellent. Excellent. That's exactly right. It does so through force of infection, I would say. Okay? Force of infection is a probability per day a given susceptible is going to get infected. So if this is a probability per day, a given susceptible will get infected, what is the formula for infection? If force of infection is the chance per day a given susceptible will get infected, or if for those interested in, in commercial sales, if it's the chance per day a given potential user of your product will adopt, what's the formula for infection? Multiplication of force of infection and susceptible, right? Okay, so let's put that into place. Let's get that in there. Let us put it in place. Okay, so we're going to have something like this, and then we're going to have force of infection, and then we're going to put in the formula as announced by Iden, which is going to be force of infection times susceptible. Is it not? Yeah, okay, good. Just trying to rehearse these things. Okay, now, remind me your name over there? Hall. So as Hal said, force of infection needs to depend on something. Okay, is that a question for me or is that a question? Yeah. Yeah.
Might be a stupid question, but
No? Yes, it is going to. It's not a dumb question at all. But in this case, you've noticed I have chosen force of infection not to be a parameter, but a dynamic variable. And that's because it will depend on other things, including, most emphatically, Ansgar, infective. So we're getting there. And I like your suggestion here. So it's going to take us to the next step here. Okay, so just as a recollection, this force of infection, if I want to figure out what's the chance per day I, as a susceptible, are going to get infected, surely it has to depend, right, on the number of infectives out there. If there's no one out there who's infective, I'm not going to get infected, right? Okay, so, ladies and gentlemen, what else does it depend on besides infective? Can anyone give me two other things it depends on, force of infection, that are in fact already in the diagram? And yeah, good. And contact rate. Yeah, excellent. Okay, so let's hitch those up. That's great. And now we have a final piece that's missing. And it's the piece to which Ansgar nodded. What is that piece? So, I have 100 contacts per day. And if I need to go from that into a calculation of if I'm a susceptible, I have 100 contacts per day with anyone, what do I need to take into account to figure out how many contacts with susceptibles I have per day? I'm sorry, with infectives per day. Yes, exactly. Percentage of people infected. So we call that the prevalence of infection. Prevalence of infection. Okay. What am I doing? Sorry. I should be in a bed somewhere in Toronto. Okay. Yeah, so prevalence of infection. Okay, great. Now, prevalence of infection, it's a fancy name for a fraction of the population that's infective. So give me something that must depend on which that must depend. Infective, surely. Okay, and then what else? Total population. Okay, now, for reasons that will become obvious in the fullness of time, or might become obvious in the fullness of time, I'm going to actually create a variable called total population, okay? And there's two reasons I do this. One is that if time allows, we might actually have population where it's not a fixed size, where it's actually varying in this very session. But the second reason is because conceptually naming something, giving a clear name to a formula, makes it model more transparent. And that's important. Like for software engineering of larger programs, transparency of a software artifact like a model or a larger program is extremely important to help lower risk of errors, to help enhance productivity, etc. So, ladies and gentlemen, we will, on what does total population depend? Give me three things. Good. Okay. Now, I'm gonna do this in a kind of longhand way here, but you'll notice it's getting a little bit crowded, and part of the art of building these models visually is just kind of managing the visual complexity. I might want to drag this total population down. Depending on your aesthetics, you might want to drag it down to here, to below this, for example, and then we have it kind of a little bit out of the way. Now, you might ask, well, okay, now we have to stretch something way up here, but I'm going to show you something new. I'm going to show you, this wasn't the primary motivator for me to fly back here, but it's a nice side effect, being able to meet with you in person. Are you ready? Okay, a component of this palette we haven't yet used, shadow. Okay, we're going to call in the shadow, and we're going to create a shadow variable of total population. And basically that's a reference to it. It allows us to use it up here without stretching a long distance arrow. Okay? So prevalence of infection is going to depend, as it was stated earlier, on the number of infectives in the total population. Great. Okay, we're cooking with gas. So give me the formula for prevalence of infection. Anyone? Good. Okay, I like what I'm hearing. You folks aren't disappointing me. That's great. It was a long way to travel, but so worth it. Okay, that's great. Okay, now, on what does force of infection depend other than what is already that to which it's connected? It depends on what? Speak as in one voice. Okay, good. Thank you. Okay, excellent. Prevalence of infection. Okay, so total population. Did we insert a formula for that? No, we need to still do that. Total population. Give me the formula for that. That should be something you could do in your sleep, even if you only got 2.5 hours so far. 2.25. I'll have it now. Okay, what's the formula? Susceptible plus infective plus recovered, right? Okay. Great. Excellent. And now give me the form. Okay, now this is something which might require a couple more hours of sleep on your part, but not notably sleep in class. Force of infection here. What's the formula for that? Give that to me. Good. Okay. Contact rate. Now, yeah, you could cut it up either way. I prefer to think of it like this, just so students are have a clear rubric in mind when they go to the final exam. Contact rate, so 100 people per day with anyone, times some prevalence of infection. What fraction of the whole population, and then by extension this group, if I have contact with 100 people per day, what fraction of them are infective? 50% of the whole population is infective, so we'll say on average 100 times 0.5 is the number of infective people with whom I have contact per day. 50 people per day, and with each of those, I have a probability of transmission chance, kick at the can. So this is going to be some representation, some approximation to my sort of probability per unit time of getting infected. And it's an approximation. It turns out that if you really think about the probabilities of it, there's actually a subtlety associated with the fact that if I'm infected from one, I'm not going to get infected from another. But it's a very good approximation when there's a low probability of transmission. Okay. And it turns out if you adapt it to the full-blown method, it works just fine as well. It's very similar. So very little difference. Okay, so this is great. That's force of infection. Now, in the crowning achievement, in what Kurt prefers not to have me call the coup de grace, what is the infection here? Well, the infection is the force of infection times the number susceptible. Okay, great. So just to sort of make sure everyone's in the same boat, mean infectious period is 10. Contact rate is 10. Probability of transmission is 0.04. We have these susceptible, infective, recovered. This is a classic first-order delay. The stock divided by mean infectious period. The total population is just the sum of the stocks, and that total population is then used together with the number infected to compute the prevalence of infection. Force of infection is contact rate times prevalence of infection times the probability of transmission for a given discordant contact, the contact between susceptible and infective, and that gives the chance per day. A given susceptible is going to get infected, and therefore the infection flow is the number of susceptible times that probability per day. Great. Are people okay with this? Are you okay? Okay? So shall we run it? What do we expect to see? Well, you tell me, before you run it, preferably. What do you expect to see? If you were to graph out the number of people infected, what would we see? Good. Okay. What does the number infective look like over time? What does the number susceptible look like over time? So actually, let's start with Howe's observation. What does the number recovered look like over time? If I were to draw that out, what would that look like over time? Starts at 0 because the initial value of that stock is 0. Good. And does it go up or down? It goes up. Okay. Does it go up linearly? Does it go up in a very fast way? How does this go up? And then slower? How does it go up?
It starts slow and then gets higher.
Starts slow, gets high, and then does it go up faster, 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 faster? Or okay, it slows down. It's kind of plateaus. How do we know it can't just go up without limit? Runs out of people. There's a conservation of people here. I have enormous respect for physicists. Some fine students of mine are physicists. Physicists talk a lot about conservation properties. And they're normally talking about conservation of mass or conservation of energy or what have you. In this case, we have conservation of people, right? People are divided up into these stocks, and they flow between these stocks, and there's no loss from the system. So recovered can never go higher than the size of the total population, 1,000, right? So it can't go up forever. It's got to have a limit to growth associated with it. Okay. Okay, so ladies and gentlemen, that's good. How about the numbers that are susceptible? How does that change over time? Does that go up or go down or wiggle around or what? Okay, so it starts high, and does it go down? In what sort of way does it go down?
Goes down fast and then slows out near the end.
Goes down fast and then slows out near the end. That's great. And does it go to 0? This is a key question. Boy, is this a nice exam question. Anyone need a piece of chalk to copy it down? It's a good exam question. Does it go to 0 always?
Perhaps it depends by the cover theory and also the
Okay. Good. Okay, I like what I'm hearing. So the short answer is, does it always go to 0? No. It does not always go to 0. Have you ever wondered why there's leftover wood in your fireplace after you have a fire? There's always some wood left over there. Why doesn't it all burn up? Well, at some point it becomes very inefficient for it to spread. It can't spread effectively. The wood around it is already burnt, and for the most part, and it can't sort of spread so completely it burns up everything. Okay? So over time, it becomes harder and harder for a given infective to infect people around them. Why? Because so many people around them are fill in the blank. Already recovered, or in fact already infective, so they can't be infective. So if I'm a given infective and I appear at the very start of this time period, if I'm the very first person who starts in the infective state, if I brought back a really nasty infection from Boston, infection none of you have seen, I could infect lots of you. Sorry, I know that sounds like an opportunity. I don't mean it as such. But I could. That's what would be the outcome with this, unusual virus. But if I were entering this class and most of you have already gotten it, I would infect very few people. I'm not going to spread it. And at some point, this becomes so inefficient to spread, it's not able to spread more. So there's typically some residual people who do not get infected by this outbreak. Okay, now, the most textured question, the question for which I wish I had a piece of colored chalk. what does the number of infective people do? And I think I'll draw this in sort of a broad sort of way. So what does the number of infective people do? Makes a hill. I love it. So it goes up very fast at first, or slower at first, and then faster, and then comes down. Something like, whoa, okay. Forgive my artistic license. Okay, something along those lines. I'm probably exaggerating how long it lasts, given how these other curves are shown. Okay, so I like that. Who said that? Who made those? Great. Name? Emmanuel. Okay. Emmanuel. So Emmanuel noted that there was this kind of rapid rise and then plateau and decrease. Okay. So first of all, let's go see if our intuitions are borne out. Intuitions sharpened, one hopes, by videos. But let's run these things out. Okay, so here we go, and we are going to run this, and we will speed this up and go view this, and we will see it rise, and we will see it fall. Okay, now, over time, let me ask my question that I asked earlier, and that Hal answered for susceptibles. I asked, does susceptibles always go to zero? And the answer is no. No, look, there's some number of susceptibles here who remain, right? Okay, that's the bits of wood left over from the fire. It's become so inefficient for a given infective to spread that it's not spreading effectively. Okay, does the number of infective people go to zero over time? Go arbitrarily small. Is that going to go to zero? Tend to go to zero? It is. It is. Going to tend to go to zero. Each of them is going to become so inefficient, they don't even replace themselves with someone who's sick by the time they recover. So the number is going down. From a personal standpoint, I don't even replace myself with, I'm infective, but by the time I recover, I haven't even gotten one person sick. And so there's fewer infectives by the time I recover on average. From a population standpoint, the number of people recovering is going to be per day is going to be higher than the number of people getting infected per day. So the number of infectives is going to be dragged down and down and down. That goes to zero. This goes towards zero, okay? So that's good. That's good. So why is it that the number infective, what's special about this place here? What is special at that peak? What equals what? Inflow equals outflow. So the number of people getting infected per day equals the number of people recovering per day. That's what's special at that peak. Is that the time when the most people are getting infective and getting infected? No. Great. And why not? Let's go run and see that, right? So this peak, okay, bit of cardio exercise doesn't hurt to keep you awake. No one that I know of has fallen asleep while running. Okay, so this occurs about time 25, right? Okay, the peak of the infective. When do you think the peak of the number of people the people per day getting infective is?
When the slope of the infection line is steepest?
Yeah, that's right. That's right. So it's a little bit earlier, actually. It's exactly, yeah, so the slope of this line is actually the fastest. The susceptible being drawn down at that time most quickly is when these infective people are the highest. So ladies and gentlemen, there's a slight difference here in the peak timing. There can be actually a big difference in the peak timing between when this is at a maximum and when this is at a maximum. Actually, this one is likely to be a little bit earlier than this one. But, so the number infective will peak a little bit earlier. Why is that? Why do I say that this flow in, its maximum doesn't have to be at the same maximum as the number of people infected? Why do I say the stock's peak could be at a different time of the inflow's peak? Because what else does the stock depend on? The outflow. Depends on the outflow. It's not just a matter of the inflow. It's a matter of what that outflow is doing, right? So that's a good observation. So so the peaks of a stock can be at very different times than the peak of the flows, right? And if you think about it, if you have a stock and it has an inflow and an outflow associated with it, that stock's peak is in general going to depend on many other things in the system than just when the peak is of any one of those flows. It's going to be different. And if you think about it, more than that, an inflow. Now, this is something to think about in terms of what we're going to see in a few minutes. If the inflow is going up to that stock, well, let me ask this. Okay, this is so if the inflow to a stock is going up, is the stock going up always?
Only if the outflow isn't going up faster than the inflow.
Yes, that's exactly right. So if the inflow to a stock is rising over time, does that mean the stock itself will be rising? Not necessarily. It depends on the outflow. If the outflow is greater than the inflow, the stock will be falling, right? At some point, if the inflow is rising quickly, it may pass the outflow, and then the stock will start to rise. But it's not necessarily the case that because an inflow is rising, the stock is rising. Nor is it the case that because an inflow is falling, that the stock is falling. That's not either the case, right? Does that make sense? Does that make sense? Okay. So a lot of basics here. Now we're going to elaborate this. Okay. So, ladies and gentlemen, we are going to go and we are going to elaborate this by adding in this formula to bring people back from recovered to susceptible. Okay? There we go. Okay, we're going to go add this in. Recovered, and we're going to call it so waning immunity. Okay, great. Look at that. And we're going to drag this down, and I'm going to double click on this, and I'm going to go frob this so it doesn't look so horrendous. So I'm going to go hitch it up like this, and I'm going to bend it in a rectilinear fashion as I am wont. So there we go. Okay, waning immunity. Now we've got a little bit of a layout issue with these things. Maybe I'll put that in the center. And for waning immunity, I'll have a mean time until waning immunity. We could say mean recovered period, but I like the sound of the clarity of this better. Okay, so this is going to be a first order delay. So what does it depend on? It depends on this mean time, and what else does it depend on if it's a first order delay? On what else? Recovered. Darn right. If ain't nobody who's recovered, there's nobody's immunity gonna wane. Okay, give me the formula for waning of immunity. The formula? Anyone? Okay, good. Recovered divided by mean time until waning immunity. Good. Mean time until waning immunity, we want to make it 270 days. Okay? 270. So its number will be 270. You notice I'm saying it, time is measured in days here. So by default, if we say 270, it's 270 days. And what enforces that is we usually do this in this flow. And a flow is a thing per day. And so we're dividing by this. And so it's being interpreted as days. We could have variables in the model of other time units, but we need to convert them into days in order to use them in formulas. Okay? Okay, so in short, ladies and gentlemen, I have a mean and time to waning immunity, which is 270. I have a waning immunity here, and the formula for that is recovered divided by mean time to waning immunity. Okay, now I want you to tell me, how does this change the picture? What's going to happen now? Cycles. Okay, so let's go take a look at these cycles, right? Okay, good. Here we go. And let's go look at infective here. Okay, here we go. Here's a rise in infective, and here we have a decline. And is it going to decline to 0? Okay. Now it looks like it's getting pretty close to 0, but what's going to start happening? Okay, so here we have it. It's still going down, but what's going on now? What's happening? It's going back up again. Crudely speaking, what's happening? Anyone? You get infections again, and now it's going down, and now it will go up. Okay, so let's try to understand these things. But to do that, let's give ourselves a little bit of a better lens again. So, ladies and gentlemen, I want to add a time plot, and I want to plot the number of infective people, just so we can see this more clearly. It's going to take a moment, but it will spare us some trouble. So, where do I go to do a time plot? Speak as in one voice. Analysis, thank you. Time plot. Okay, here we go. Time plot. Let's go put her in, and let's go call it plot stocks. Okay, great. And we need to add a data item, and that item will be initially, we'll put in infectious, and we will put in infective individuals, and then we will also plot out the others. We will plot the susceptible, and we will plot the recovered. So I'd like you to put all those in the time plot. You can choose colors of your liking, and then we can, maybe for consistency, let's make infective red, and let us make susceptible here green. Susceptible, and you notice I'm doing control space, I think it's option space on yours, and then finally we will do recovered, which will be gray. Okay, recovered. Notice that the title is simply a string. I could choose as I see fit, but I've simply said to call it the same thing as the stock. That needn't be the case. Okay. Oh, and then to further resolve this down towards the bottom, I want to do display up to 1,000 latest samples. Say 1,000 latest samples with a time window of 1,000. Okay, model time units. Fine. Okay. So I'd like you to run this. So again, this is the scale, and then just above that, display up to 1,000 for the data update. Okay. Okay, so let's run this thing. And what do you think we'll see once we see it on the big screen, so to speak? What we see in this graph, writ large? What do you think that red will do? Who can prognosticate? Okay, so now we see a second sort of outbreak, now we see a sort of third one. But it's going to some point. Where is it going? Where is it going towards here? Well, okay, let's first reason about what are we seeing. Okay, so this stock here, this is a peak in infectious. What's driving that peak? Anyone? What's driving that peak? In infectious. Anyone? This first peak in infectious, this peak of red, what's going on there?
Inflow equals outflow.
Okay, at the maximum inflow equals outflow, right? That's when it's flat, right? If this equals that, in fact, it won't be changing. That's right. Why does it rise quickly initially? Sorry? Yeah, lots of people susceptible to get infective, and therefore those people can be infected very quickly. You can get a rapid rise of it. Why does it peak out? Why doesn't it continue to rise really quickly? Sorry? Saturation. Yeah, there's fewer and fewer infected people around. Each new infective can infect fewer people around them, right? So the number of people getting infected is not rising nearly as quickly. And more than that, what else is occurring? As this is rising, what else is occurring? More and more people are recovering. So the excess of infection over recovered, which is really what's changing infective, becomes smaller and smaller. So it's rising, but it's rising less and less quickly. And as it rises less quickly, the number who are getting infected is going to increasingly rise slower and slower. Why? Because, well, you're not doubling the number of infective, and the number of susceptible are dropping very quickly. So the number of people getting infected is not rising all that quickly pretty soon. We have fewer and fewer susceptibles to multiply by force of infection, and the force of infection is not rising all that quickly, and recovereds are rising. So because of that, it rises up to this peak, right? And then it starts to decline. Now, what's going on here? This is absolutely key, and I want you to really nail this. What is going on as this number of infectious is dropping? Why is it dropping so quickly? Give me two reasons it's dropping quickly. Give me two reasons in this early part it's dropping very quickly here. Very few people to infect. In fact, the number of people that can be infected is itself dropping quickly. The number of susceptible is dropping quickly as well. So there's fewer and fewer people that could be infected during this period that infection is dropping. And there are fewer and fewer people to infect them. Right? So during this period, why is infectious dropping? Well, it's dropping because there are fewer and fewer people getting infected and lots of people recovering still. And these people getting infected, that depends on the number of susceptible, which is dropping quickly, and the number infective, which is dropping quickly. So for both those reasons, the number infective is dropping quite precipitously during this time. Now, watch this. This is a key thing. So the number infectious comes down like this. Number infectious comes down, but the number of susceptible, even as the number infectious is coming down, the number of susceptible is also declining still. Why is that? Why is the number of susceptible still declining with the number of people, even as the number of infectious people declines? There's still people getting infected. I mean, there's very few people waning immunity, and there's lots of people there's quite a few people getting infected. So it's going to be going down. Yeah, okay, maybe the number of people getting infected is going down per time unit, but it's still greater. This outflow is still greater than what? Than this inflow. And so the number of people susceptible is going to be dropping during this time. But why does it, even as number of people infectious is still continuing downwards, why is it that susceptible starts to pick up? Why is it that it's picking up here? Yeah, more people are, well, they're waning immunity rather than getting infected at this point. So susceptible starts to rise here, not because the number of infections per unit time starts to rise. That's actually not the case yet, but it's because the number of susceptible is rising because the waning of immunity, loss of recovered population, exceeds the rate of infection, and so susceptible is going to rise. Now, if susceptible is rising, why isn't infectious? Why isn't the number of people getting infected per unit time rising? Well, let's go see that. I'm simply saying it's not rising. Let's go create a similar plot, ladies and gentlemen, that shows just the number of people getting infected per unit time. In other words, infection. So let's take a little bit of time to do that. Go to time plot here, and let's go drag this out, and we will go, and we'll have to go, and we'll call it plot flows, and let us go plot here infections, okay? Infections. And we will plot this also in red, reflecting the fact that it's associated with infection, and it will display up to 1,000 samples with a time window of 1,000. Okay, we're in good shape here. So what did I just do? I added this plot, and I had it plot infections. Okay, great. So that's the number of people per unit time. So let's go see that. So let's go run this thing here. Okay, it's an unhappy camper. Infections, okay, what did I call it? Did I call it infection? Was that what I call it? I called it infection. Okay, come on, great. Okay, infection. Okay, so let's now run this thing. So it's a happy camper, build early, build often, and now let's run it. Okay. Okay. So let's go check it out. So as this rises here, we have this peak, and you notice that this turned a little bit quicker than the stock, it appears. But you notice that this rate of infections is still declining, even though susceptibles is going up. See that? It's going up, but rate of number of people per week getting infected is still going down. Why is that? Why is the number of susceptibles rising, but the number of people per day getting infected is going down? Yeah, there's not many infectives to infect those susceptibles. So this susceptibles now this is, again, essential. These susceptibles build up to a much higher level. While infections is going down, the number of susceptibles can rise up quite a bit. And that sets the stage for this next outbreak. This sets the stage where you have lots of susceptibles, and there can be this rapid growth in the number of infections associated with them. So there's this stock and flow dynamic, ladies and gentlemen. Long after the susceptibles is rising, the number of infections is still going down. Even though the number of infections is declining, the number of susceptibles can also for a while be declining. Because what matters for a flow is not the value of one flow alone, it's the net value of the flows. It's inflows minus outflows. Susceptibles will be going up if what? As a general rule, be going up if the waning immunity is greater than the infections, the rate of infections. The rate of waning immunity, people per day, exceeds number per day who are getting infected, it will rise. And that's what we're seeing here. We're seeing that susceptibles is rising all through this period, say around time 100, even though the number of this is rising, the number of infectious individuals, number of infections, the number of infectious individuals is still going down. It's still going down because it depends not only, infectives depends not only on infections, but on recovery, and recovery is still quite large. So we have this stock and flow dynamics, and these dynamics, these delays associated with this dynamic lead to these oscillations. There's a certain amount of time where susceptibles can build up, and number of infections hasn't yet shot up. And as a result, it can build up to a level that exceeds its sustainable level, and that can cause a second outbreak. It declines, and it can again build up to a level where it exceeds the sustainable level, and that causes a third outbreak. In general, within this system, there's a sustainable level, but because of these delays, you can get these oscillations. And you may remember, back when I was talking about causal loop diagrams, I argued that when you have a negative feedback with a delay, it can lead to oscillations, and this is a good example of that. Yes, Ansgar.
At the beginning of the class, you showed us some real-life
Yes.
outbreak patterns.
Indeed.
And what we saw were these repetitive peaks.
Exactly.
We see this goal-seeking equilibrium behavior.
Yeah.
Is our model missing to get these reoccurring peaks?
It's a great question. So the answer is those peaks are associated with the same phenomena, okay? At a broad level, those recurrent peaks are associated with the same phenomena, but you'll notice that they are exhibiting far more pronounced sort of repetition with very low rates in between. I'd like to do an experiment which will start to get us some insight there, but it turns out we're going to focus on that in a problem set, okay? But first, let's go and take this model and let us go change this. I would like to create a new experiment here. So you can go do new experiment, and I would like to set long waning time, okay? And instead of doing 270 days, I would like to do 500 days, okay? What do you think the difference will be now? Think about it. What's going to be going on? What is it that it allowed? So building up of susceptibles allowed what to happen? A second outbreak was permitted because susceptibles rose to a high value. Susceptibles will be recovering in this new case, but it will take a long time for it to recover. Why? Because it'll be a long time before the waning of immunity starts to build up large numbers of individuals. So let's go see what starts to happen here, Ansgar. Okay, so now we have a very, very small decline here. And susceptibles is building up here, actually. So it is building up through this period. But the second outbreak is substantially delayed. But it's still not as big as the long one. We have delayed it. It could be a little bit bigger than that first time, but it's still not as sharp, Ansgar. So if we wanted to add that, we could do so in a couple of ways. And broadly speaking, the key factor that leads that to happen, Ansgar, is actually there needs to be a certain number of susceptibles for it to start to really spread efficiently, okay? And we could put that in as a restriction here, that essentially it's instead of just having susceptibles times force of infection, instead we will have a function of the number of susceptibles that means that it's a slower force, it's a smaller number of susceptibles that spread the infection unless you have a certain the number of people getting infected will tend to be very small unless you have at least a certain number of susceptibles. It turns out that the full answer to your question involves networks. And we will look into capturing those networks in our start on agent-based modeling either next time or the time beyond. That will allow us to start working towards capturing networks and network structure. But to really account for that, you're not going to be able to account for it just by adjusting parameters with this model. You're going to have to adjust this model in some way to posit other effects. I think the most plausible one would be an effect associated with the density of people who are susceptible. And unless you have a certain threshold, it's not going to spread. But as we will see in an agent-based model, that's because there need to be bridges, susceptible bridging, say, one group of susceptibles with another, so the infection can spread between them. Okay, we'll see that. But suffice it to say that those peaks that you do see are exactly representative of these peaks here. It's just that they have additional texture in the processes that give rise to them, and therefore they're more pronounced. But they're the same basic stock and flow phenomenon. What leads to a peak to sort of happen in one year and then not happen for a while and then happen again is in between these periods there's a buildup of susceptibles. It's the buildup of susceptibles that allows that later peak to happen. And because that buildup doesn't occur immediately, that new outbreak doesn't occur immediately. So here we have stocks, flows, delays associated with the buildup and with the decay. And these delays are reflective of the fact that a stock is not at its maximum at the same time its inflow and outflow are at their maximum. Okay? There's delays here. The inflow can be rising, but if the stock's outflow is still bigger than the inflow, like for infectives, the number of infectives might still be declining even as the inflow, for example, might be rising into it until it reaches that key point where inflow is greater than outflow, and then the stock will rise. Okay, so that's a key point. So, ladies and gentlemen, now what would happen if we were to change this model to take into account a non-closed population? What is going to happen, do you think? So suppose there are births and deaths. Suppose it didn't. Suppose it was flu. Well, not flu. Suppose it was common cold or something like that, so it doesn't. Good. 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 Let's suppose all of them with a certain rate. Say, maybe our model is just focused on youngest 5 years, in which case the flow out in an average of 5 years. Maybe it's focused on people 18-year-olds and less, and they flow out in 18 years on average. Maybe they're associated with a full lifespan. You divide, and you have outflows, first-order delays out of each of these stocks associated with the mean lifetime of a person out of each and every stock. So let me ask this. Suppose the number of deaths, the rate of deaths, the number of people per unit time leaving the model, 1,000 people per year leaving the model, 1,000 people per year coming in. Is that the same as having no deaths and births in the first place? In terms of the dynamics? No. Why not?
Because there's 1,000 people going to susceptible every day.
Yeah. They're all going to susceptible. And so you're getting this inflow of susceptible. It's like you're putting fresh wood on a fire, right? You're throwing in fresh wood into this fire. You keep the fire going, right? You keep it going. It's the presence of susceptibles that allows these outbreaks to keep on going. If there's few susceptibles or it can't spread effectively, it will tend to peter out because it can't jump. I can't replace myself with another infective by the time I recover. Or put differently, in terms of the number of infectives, if there's no new susceptibles, number of infections is going to eventually decline below the rates of recovery. Infectives will go down. As infectives goes down, the number of infections goes down, both because this is going down and because susceptibles is also declining, and we're going to have that drop precipitously. So, ladies and gentlemen, it is most certainly not the case that if you have births and deaths equal, that it's the same as having neither. You most certainly do have a big difference if you have births and deaths because they're coming into susceptible. Okay, so that's an important observation. Now, I'm going to, as a teaser for the next video that I'm going to ask you to watch, I'm going to ask you, suppose we wanted to write this down as a set of formulas that could then be solved, a set of equations. So this is contact rate. I have beta, which is the probability of transmission per discordant contact of transmission, right? And I have this mean time, mean infectious period. Let's call it delta. So this is mean infectious period. And then I'm going to have mu, which is mean time till waning immunity. Okay? Okay, great. I could write down, it turns out, formulas for this model in terms of the rate of change of these stocks. So the rate of change of stock S, which we write as S dot, how quickly it's rising in people per day, is going to depend on what here? Anyone? What is it going to depend on? Well, let's start with an easier one. Let's start with R. What is R going to depend on? Well, it's going to depend on number of infectious period divided by this mean infectious period. That's just the formula. Okay? So here we have flow in to this. So this is a plus associated with that. And we have a flow out, right? Flow out associated with the number of recovered divided by mean time to waning immunity. Do you see that? So the rate of change, how quickly this is going up per day, going up 5 people per day because there's 10 people per day coming in and 5 leaving, right? So 10 people per day coming in, 5 leaving, so this goes up 5 per day. For infectious, do you want to give me the formula? Part of it is here already. Minus I over delta, because you have a flow out of infectious people by recovery, right? And what's the flow in? Well, the flow in is into infectives is what? The flow into infectives is good. Susceptible times force of infection. So I'll take I times, and let's break out force of infection, the contact rate, times the prevalence of infection, I over S plus I plus R. Yeah. Okay. Times beta, right? Right? This is the force of infection here. You recognize that? C, right? Okay, yeah. Force of infection, contact rate, C. Prevalence of infection, right? Prevalence of infection, beta, probability of transmission, right? Right? Times the number it's susceptible. Where'd that come from? That's this formula. Susceptible times force of infection. So this guy here is the force of infection, the FOI, or lambda as we call it, typically, and it's times S. And so can anyone give me the final formula for S here? Can anyone give this to me? What's the flow into S? We actually have it down here already. R divided by mu. Where did that come from? Where did that formula come from this? It's right here. Right here. Recovery divided by mean time. Recovered R divided by mean time to waning immunity. That's that formula, right? That's the flow in. And the flow out is what? What's the formula for flow out? We have it here already. S times C times I over S plus I plus R times beta. This again is the force of infection, and this is the number of people susceptible. So we can write this out like that. Now here is the final question for you. Here is the final question, and I will wrap this up. If we wanted to see what's the long-term behavior of this model, where it is not changing over time, the stocks are no longer going up, no longer going down, what does that imply about S, the rate of change of S? If that stock is fixed, it's no longer fluctuating, it's reached its equilibrium where it's in balance. What equals what at that point of balance? If a stock is no longer going up, no longer going down, if it's plateaued, what equals what? Its inflow equals outflow. Its rate of change, how many people per day by which it's rising is what? Zero. So at equilibrium, at this state of balance, at this kind of long-term steady state where it's in balance, S dot equals I dot. Okay, I like that. I like brevity equals R dot equals 0. This is not rising, it's not falling. It's staying the same. It's not rising by 5 people per day. It's not falling by 5 people per day. If it was rising by 5 people per day, S dot would be 5. If it was falling by 5 people per day, S dot would be minus 5. Instead, it's 0. So at equilibrium, what I call the fixed point, the point where it's in balance, it's in stasis, it's not changing. You have S dot equals I dot equals R dot, right? And watch this. You run this, and you will see, boom, there it is. That is equilibrium. So if we assign these here, S dot equals I dot equals R dot, if we set these equal to 0, we could solve for the values of the system. What's the value of S, I, and R in terms of these parameters at which it's at equilibrium? In other words, we could find what is the value of S, that's the green line, R, that's the red line, and the gray line, R is the gray line, and infectious I is the red line. We could find what those values are as a function of the betas, of the C's, of the mu's, and of the deltas at this equilibrium. That's when it's in balance. And that video, I'm going to ask you to do that, and in one of your problem sets, you're going to be asked to do this. Find the points of equilibrium. And the answer is there's typically more than one. One is this endemic equilibrium where the infection has stayed in the population, and the other is a situation where the infection doesn't exist in the population. Everyone is susceptible, no one's infected, say no one's recovered, there's no new infections taking place. So that's all for today, okay? but that's where this is going, the ability to calculate it. And after that, we're moving on to agent-based modeling. Okay? Yeah.
So I decided on the project idea that I
Great.
wanted to do.
Good.
And I wanted to ask
Excellent.
when I should sit down with you and run through it and finalize it and get the
Well,
first,
are you free now?
Yes, for a little bit, yeah.
Okay, we could talk now.
Okay, sure.
Would be a good time. We have S386 reserved. If anyone would like to go to office hours, I'll be holding them there.
Sure. Okay.
So I'll be there in just a minute. Yeah. Yeah.
So I was traveling last week. I didn't get back in until
Okay.
Monday night.
Okay.
I totally forgot about the assignment.
Okay.
I for some reason thought it was due at the beginning of October.
Okay.
I probably mixed it up with some other stuff.
Okay. Okay.
I'm just wondering, can I still submit it? Will I still get some March, or will I get like?
How quickly could you submit it?
I'd say tomorrow night. I have to work at night, so I don't really
Okay.
have time tonight. But well, I can
Okay.
maybe do it tonight even. But
Okay. Okay. So get her in by tomorrow night. Okay.
okay.
Okay. Your name? Chris. Okay. Last name?
Morose, Morose.